off the day right. Now you may be asking, what am I doing here? Well, I'm gonna be for real with y'all. I said that I was gonna see if I could try to do a school stream. So I woke up at 7 and I put the Chick-fil-A uniform on. Now, we're gonna go ahead, I'll read the Bible, start our day off right, and do good things. Alright, that being said, we're gonna be reading out of Ephesians 5. And that's what I guess it says. And imitate God, therefore, in everything you do, because you are his dear children. Live a life filled with love, following the example of Christ. He loved us and offered himself as a sacrifice for us, a pleasing aroma to God. Let there be no sexual immorality, impurity, or greed among you. Such sin has no place among God's people. Stories, foolish talk, and coarse jokes, these are not for you. Instead, let there be thankfulness to God. You can be sure that no immorality, impurity, or greedy person will inherit the kingdom of Christ and of God. For a greedy person is an adulterer, worshiping the things of the world. Good morning, medicine. We're reading the Bible today. We're in Ephesians 5. We're going to read the whole chapter and get ready with our day because we got work. I mean, not work. We have school at 8 o'clock, then we got work. So it's just kind of like a day in the life. But let me continue. Ephesians 5:6 says, "Don't be fooled by those who try to excuse these sins, for the anger of God will fall on all who disobey him. Don't participate in these things these people do, for once you were full of darkness, but now you have the light from the Lord. So live as people of light, for this light within you produces only what is good and right and true. Carefully determine what pleases the Lord. Take no part in the worthless deeds of evil and darkness. Instead, expose them. It is shameful even to talk about the things that ungodly people do in secret, but their evil intentions will be exposed when the light shines on them, for the light makes everything visible. This is why it is said, 'Awake, O sleeper, rise up from the dead, and Christ will give you light.'" So be careful how you live. Do not live like fools, but like those who are wise. Make the most of every opportunity in these evil days. Do not act thoughtlessly, but understand what the Lord wants you to do. Do not be drunk with wine, because that will ruin your life. Instead, be filled with the Holy Spirit, singing psalms and hymns and spiritual songs among yourself, and making music to the Lord in your heart, and giving thanks for everything to God the Father in the name of our Lord Jesus Christ. And further, submit to one another out of a reverence for Christ. For wives, this means submit to your husband as to the Lord, for a husband is the head of his wife, as Christ is the head of the church. He is our Savior of his body in church. As the church submits to Christ, so you, wives, should submit to your husband in everything. For husbands, this means you love your wives just as Christ loved the church. He gave up his life for her to make her holy, clean, washed by the cleansing of God's word. He did this to present her to himself as a glorious church without a spot or a wrinkle or any other blemish. Instead, she will be holy and without fault. In the same way, husbands ought to love their wives as they love their own bodies. For a man who loves his wife shows love for himself. No one hates his own body, but feeds and cares for it. It's just as Christ cares for his own church, and we are members of his body. As scripture says, a man leaves his father and mother and joins to his wife, and the two are united into one. This is a great mystery, but it is an illustration of the way Christ and the church are one. So, again I say, each man love his wife as he loves himself, and the wife must respect her husband. Alright. Eat a Chick-fil-A. What am I reading? I'm reading the Bible. I read Ephesians 5. This is the day in the life, bro. We pulling up to school like this. But yeah, I said because I got off Fortnite and because I played Fortnite at like 2 o'clock and I had 5 hours of sleep. But I'm actually feeling pretty energized today. Yo, what's good, y'all? So we're gonna like brush our teeth, get ready for the school. Peep the first day of school drip right here. We got the Chick-fil-A uniform. Yeah, it's okay if you fart. I think we all fart sometimes. I'm gonna be for real with y'all. How y'all doing, chat? I have a good setup. I was reading the Bible this morning, if y'all aren't here. What do you think about the Chi skin? Oh, I don't have that skin. I think Cypher PK goes crazy over that skin. W hair, bro. Thank you. I woke up, bro. I'm not gonna lie. I'm gonna put y'all on. Y'all need to take cold showers and just let that air dry and make sure it's not wet when you go to sleep. Because when your hair is wet, if you go take a shower after you sleep and you roll around in it, it's like it gets wet and it gets used to it, and then you have like really bad bedhead. But if you just take a cold shower and just let it air dry, I'll be good for you. But let me brush my teeth and wash my face real quick. Then we gotta head over to school, take some vitamins, and maybe eat some eggs. Mm. Hmm. 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 Going to school in Chick-fil-A uniform. Going to school. We're just gonna try to live stream as much as I can, even at school. I'm not sure. My teacher seems pretty cool, so. No, I rushed for like 2 minutes, so it's gonna take like another minute, you know what I'm saying? White Cardi? Yeah, I'm White Cardi. What's up, Team Dragons? What's good, huh? What's up, bro? What's good? What's up, bro? Everywhere here? Nah, y'all some W's in the chat. I appreciate y'all. I love you guys. What am I saying? I'm saying I love you guys. I say y'all from W for real. So, W's in the chat. You know what I'm saying? We grinding. We would pull up to school like this in a Chick-fil-A. Give me chicken nuggets. Bro, I got you. I think I could get a Chick-fil-A nugget. I don't know how it works. You got the Chick-fil-A app? I don't know if I have enough points. I just waste all my points. You know what? If I use the Chick-fil-A app, I'll make sure to give y'all points. I'll do a giveaway nuggets. Well, my teeth feel so nasty right now. I have to brush until like I don't feel nasty. Yeah, I have. You need nuggets? After you keep this, I'll like and subscribe. Thank you. Y'all some W's in the chat. Man, that's about 2 minutes. What? I tell you, the Hutsu girl did not have it before me. I've been doing it ever since I brushed my teeth, bro. I don't want to say that. I should have done that. I was going, what? Every single time. Like, no weird stuff. Like, she made it weird, but that was me. That was me. All right, hold on. Thank you. W's in the chat. Okay, now we gotta wash our face. All right, here we go. This is basically day in the life live stream. I bet you never seen this before. Yo, what's up, brothers? Can y'all hear me right now? Because I'm pretty sure like the microphone of the phone is on the ground. Um, Chat. Stop trying to troll me. That's what's it called? That's Steve Kerr's son. Go wish Steve Kerr's son, Nick, last name, uh, like Korean, but without the Ian at the end. A good, time. You know what I'm saying? Yeah. Bro, that'd be the craziest clip farm. If I wanted to clip farm, I'd really say it, but I'm chilling right now. And just give the shout out to my friend Nick, last name Korean. Take a super. I wish I had a super chest, bro. I gotta get like my hours up. Like I have 1K, but I gotta get my views up and my hours up. So trying to get my watch time hours, so I'm trying to live stream. Do you follow? Yes. I feel you guys don't need to do that to yourself. Because like it's not good for you. Yeah, we'll say it. I do know him. It's bad. It's just lust. It's not good for you, bro. You gotta pray and repent that you don't do that stuff. That's the only way out of it, bro. I'm gonna keep it a buck. It is not good for you. As men, we've always been there, bro, but don't do that. I'm gonna keep it a buck. Alright. Just showered. I have school tomorrow. Wait a minute. But today's Wednesday. Oh, yeah, man.
I love you.
I love you, Mom.
All right, have a good day.
You have a good day, too. Love you. Turn out the lights. We live right now. What's up, dog? Chat, this is dog. This is a dog. That's my dog for real. You just showered? No. I'll give y'all a pro tip in the morning, which I need to do. Read y'all the Bible, pray, and then make your bed. You have accomplished so much in that amount of time, and you're gonna feel good. I'm off of 5 hours of sleep right now, and it's by the grace of God that I have energy like this. But I am currently 19. I'm finna pull up to college. Alright. I clean my bed. I don't sleep it too messy. I'm trying to think of what I need before I dip out of this joint. I need to make sure I get my chug jug. Y'all gotta see that chug jug. Bro, why am I... Ugh. Chat, we going. Bro, you failed your test today. Is there a retest for it or no? Are you just like utterly done with it? Cause just like study and retest for it. Cause you already know it's gonna be on the test if you just retest it. Let's figure out what the answers are for.
Hello. Call Riley Payne.
Calling Riley Payne mobile.
Does it work now? Can y'all hear me now? Chat, we're gonna have to re-up this live stream. If y'all can't hear me, we're already having problems. Yes, you can hear me now. I'm not gonna lie. I just definitely fell down the stream. Alright, chat. I'll give y'all an interview. This is school. We out here, 7 minutes till class. We secured the Pokemon snacks for real. I'm personally a Scooby snack person for real. Code word Scooby snack for me is a Chick-fil-A sandwich, but I'm not gonna be eating any of those anytime soon. I'm gonna just ask her if I can record the lecture, and if I can't, then I have to end it, most likely. Good morning. How you doing? Just trying to split the Red Sea, but I forgot the password. How do I reset it? I do not know. Is there a certain place we put our homework?
I'll ask for it in a minute.
Okay.
Like a lot of work.
Yes, ma'am. Let's make sure. Yep. I remembered it. Let go.
That's the only class I have. Don't start until you
Be in the front of the class right now. Need no book. Let's see if we can find any open pages in here. Welcome back now. Yeah. We made it to class, chat. I made it. Let's see if we can get through this. Where are you at, my brother? We in class right now. We here. We here right now. Look at this. We here. Back at it. We got what's it called? Pokemon snacks. I'm recording my teacher doing Albert Einstein. That's crazy. Yeah. Let's see if we can stream in class today. I try for y'all. I'm dead right now. I think I've fixed up the mic glitch. So. Alright. Bro, all my pages are filled up. Low key. Like, I don't got enough space or storage in this notebook to take notes. Hey, what's up? I'm Jay Handsome. No, you. Thank you. I appreciate it. We at school right now. We're gonna see, if we can live stream class. I noticed me recording and scaps my hand under the ruler. Dang, I don't understand. So I'm pretty sure the mic is working right now. Could be wrong. Well, we have the front of class with this, so this may be a little difficult. Well, yeah, we just be learning class right now, doing our thing. I'm mainly gonna be like this. I'm gonna have to be quiet during because she's gonna be talking. So if I go quiet, then I'm just gonna be quiet, guys, because I'm here to learn. I'm also here to entertain if I can, if you know what I'm saying. I ain't gonna be doing nothing stupid. I can't get expelled out of here, but I don't think they mind if I just record like this. Your age? I do happen to be of age. I am 19. Chat, I just leaked. I would say and you, but I feel kind of scared because you asked that question. just leaves chat. Noah's here. They gave us free Pokemon snacks today. We're in like physical geology today. After that, straight to Chick-fil-A. Dude. And some. I did. Can y'all hear me or no? I said that you said, OMG, you're so handsome. I said, no, you. Nah. It's Chick-fil-A. We're gonna work on that. Hold on. Bruh, it's just a day in the life. It's day in life stream, to be honest. It's gonna be a Chick-fil-A stream. It's me going to it's morning routine then to going to work. Quite frankly, I actually go into school with my Chick-fil-A uniform on, but class is about to start right now, so let me log in. Please ban me. What time and which country? That's crazy. Maria, did you go? I'm from the U.S. Wait, no, why do you want to be banned?
No.
Please ban me? Okay, maybe it's a... He wanted to get banned. Maybe it's for a speed run or something. Alright, time to look in chat. At school right now with Chick-fil-A uniform. Good morning, brother.
Good morning, dog.
So, don't pay attention to the clock. The clock's broken. We'll be here forever. It's very slow. So, it's time for class.
Okay.
First of all, I'm gonna call roll again. I'm still learning names. I'll do my best. I really, honestly, will learn everybody eventually, but it'll take me more than a day. Let's see. Benjamin Alvarado. Braylon Antwine. Manuel Benitez. Paige Birdsong. Caitlin Brand. Joshua Sichersky. Emiliano Contreras. Micah Creamer. Samantha Queller. Leah Davis. Kevin DeGante. Andrew D'Amatos. Jimena Esparza. Paulina Gonzalez. Jacob Harrison. Andrew Lozano. Gavina Martinez. Crystal Miller. Jessica Nettles. Oscar Nee. Nathan Odenbach. Zyder Umpad. Riley Payne.
Here.
Joshua Paras. Marifer Rosales. Randy Soto. Andrew Tucker.
Here.
And Morgan Vaughter.
Here.
All right, great. Okay, now before we do anything else today, before we get into class, and then ultimately we will start a lab today, you had homework last time. And before I ask you to hand that in, are there any questions on the homework? Do I see a hand back there? Yes. What was your name again? Marifer? Yeah. Okay, Marifer, what's
I
your
like
question?
math. That's my favorite subject, Chad.
Number 6.
Bro, I literally got off at Fortnite at 3 o'clock in the morning. I'm not gonna lie. I had to get a win and reload. We did get it done though.
Had to.
It was just that type of day. I just decided I was gonna do a day in the life today.
So
Just gonna try it out.
Inner planets have a different composition than the outer planets. Anyone want to answer that? All right, go ahead.
So because they're made of refractory materials, they have a higher melting point.
And why is that important, that higher melting point?
Because it can withstand like the sun's heat.
Perfect. So that's the big answer that I want you guys to get at is the inner planets are made of these refractory materials, that means minerals with a high melting point. And they can have that composition because they are close to the sun where it's hotter. The outer planets are made of the stuff that has a low melting point, it's stable where it's colder, so those are going to be farther from the sun. So it really has to do with the distance of the sun controls their composition. Any other questions on the homework? Any other questions? No? You sure? Okay, then make sure you have that answer put down and hand your homeworks over this way. And I will get to grade it for you. When it comes to homeworks,
I think she said minerals with a high melting point are the inner planets or the outer planets?
The outer.
Minerals with a high melting point.
Farther have lower.
Okay. So higher is outer.
Just when you get it written down. Alrighty. Yeah, great. Oh, and then some right there.
Thank you.
Oh, thank you very much.
My pleasure.
All right. Now, next up on things to go over is today we're going to have a lecture on minerals because we're going to start talking about what the Earth is made out of. So the way the class goes for the semester, the first couple weeks we're going to talk about what the Earth is made out of, the rocks and the minerals. Then we're going to look at big picture concepts in geology, like plate tectonics and Earth's interior. And then we'll go into natural hazards, volcanoes and earthquakes and stuff like that. So that's what you can expect over the course of the semester. But today we're going to be learning about minerals, and you will have a homework over that. But if you notice, it's due a week from today because Monday's a holiday. It's Labor Day.
Lego.
And so there's no school. So don't come to any of your classes on Monday. All right, in that case, let's get around to lecture then. And we'll start class with lecture, and then we will, for the second half of class, be starting a lab. But I do not expect you guys to finish this lab today. It is a longer lab. You'll have plenty of time to finish it. But we're going to be looking at these things. So minerals, what all of the rocks and all of the solid part of the Earth, what the geosphere is made out of, come in all different shapes and sizes and compositions. And they form in different ways as well. but not everything that's solid on Earth counts as a mineral. Not every substance Earth makes. So in order for something to be a mineral, it has to fit 5 characteristics. So if you're ever like, I wonder if it's a mineral, just follow this checklist. If it fits all 5 things, then it is. Number 1, it needs to be naturally occurring. Nature has to be able to make this substance. It can't be just something that we artificially create in a lab under special circumstances. So nature has to be able to make it. It's inorganic, and when we're talking about inorganic, that's referring to, in the structure, carbon-hydrogen bonds. Now, I'm not saying you can't have carbon in the mineral, I'm not saying you can't have hydrogen, but you can't have these carbon-hydrogen bonds together in there. Now, I also up there it says usually, because there's a couple of exceptions to that rule. But they're very, very rare. So you can basically think a mineral is naturally occurring and inorganic. Next up, it's got to be solid. If it's liquid, it's like water, not a mineral. Must be solid. But more than just being solid, it has to be crystalline. Now, crystalline refers to how the atoms are arranged in that solid. A crystalline solid has a regular repeating pattern of atoms. It's not all chaotic and random. So what this illustration is showing, we're using these little ping pong balls to represent atoms. And notice here, there's no pattern, right? It's completely random. Over here, in either one of these, there's a pattern that repeats itself. So that would be crystalline, right? There's a regular repeating pattern. This is not crystalline. So that could be a mineral. This would definitely not be. A solid that does not have a crystalline pattern to it, that's very common, is glass. Lastly, minerals have a well-defined chemical composition. That means we can write a chemical formula for it. We can write like NaCl, and that's, you would know it as salt, but in geology we call it the mineral halite. But all minerals have a chemical formula because they have a well-defined, they have a definite chemical composition. So, like I said, if you're ever wondering, is this thing that I have a mineral? Well, go through that checklist. If it fits all of them, the answer is yes. If it doesn't, then it's not. Any questions yet? No? All right, now when you guys come to me, I know some of you have had chemistry classes, and some of you haven't, and some of you had chemistry, but it was like 14 years ago. And so because minerals are chemicals, right, they have a chemical formula, and when we're looking at how they form, we have to look at how atoms bond together and things, we need to have a little chemistry review. That's for people who've had chemistry, or this is an introduction if you haven't had it. So we're going to keep it real nice and simple. Hopefully this stuff is familiar to you, but if it's not, that's why we're having this nice little introduction or review. And one of the things you have to know is what an atom is. And an atom is the smallest particle that exists as an element. Again, I don't have a periodic table of the elements in here, but you know, elements are things like gold and silver and copper and, I don't know, hydrogen. And so an atom would be the smallest possible particle of like gold you could have. If you break that apart, you no longer have gold. If you break apart an atom of copper, you no longer have copper. It's the smallest thing that exists as one of those elements. But atoms are made from other things. And we call these subatomic particles. Sub means smaller than, right? So it's smaller than an atom. And in atoms, those have a positive electrical charge. You have neutrons. Those are little particles that have no electrical charge. And then you have electrons that have a negative electrical charge. And in our classic simple atom, there's a center part that we call the nucleus. And that's where the protons and the neutrons hang out. And then you have the electrons that orbit. They basically move around the nucleus. And it depends what chemistry class you've taken. They will call these electron shells. I've heard it termed electron levels. I've heard it valence levels. There's various terms, but I call them electron shells. Each shell, so there's multiple ones, almost like how we have different planets orbiting around the sun, right? Well, the nucleus is the center, and then we have these different levels orbiting around there. And each level can hold a certain number of electrons. The first one can hold up to 2, but no more than 2. The second one can hold up to 8, but no more than 8. The third one also 8. And so each one has a certain number of electrons it can hold. Now the reason we care about this is because the number of electrons in that outermost shell determines which atoms like to hang out together and bond. And when they bond, they make our minerals. So that's why we care about that. Are there any questions about this? Okay. All right, now I used that term element a little bit earlier. And an element is a substance that cannot be broken into a simpler substance by ordinary chemical or physical means. Ordinary means something I can do in my garage. We can break these apart, but we need very extraordinary things to do that. And you hopefully are familiar with the periodic table of elements, where there is something like 117 of them, and each individual one has an atomic number. And the atomic number is the number of protons an atom has. And that number of protons is what makes it unique. So we talked about hydrogen in the sun Monday. That always has 1 proton and never more. Because if it has 2 protons, it's not hydrogen, it's now helium. And if it has 3, it's now lithium. So it's that number of protons that defines each element. And that's where we can see it here, right? In this particular periodic table, in the upper left-hand corner, that's the atomic number. So you can see hydrogen 1, lithium 3, cobalt's 27, arsenic's 33, and that's what makes each one of those unique. Ooh, I need to update my periodic table.
We got some new elements or what?
Yes, I just noticed that. All right, all of those, if we look at this again, and you don't need to read these little numbers that are down there, but there's another number on there. That's called the mass number. And the mass number is the number of protons plus the number of neutrons. It's basically, I mean, the way you can kind of think of it, it's how much each of those different elements weighs. It's a simple way of thinking of it. Now we ignore the electrons because the electrons, their mass is so infinitesimally tiny, we can ignore it. We can just skip that. So it's always the number of protons and neutrons. Now, different elements have what are called isotopes. And an isotope is a variety of an element with different mass numbers. And right now, today, we're not really going to spend a lot of time talking about isotopes, but a little later in the semester, they're going to become important to us. And so I'll give you an example of an isotope or isotopes around us right now, and that's in oxygen. So oxygen, every oxygen atom has 8 protons in it. But some oxygen atoms have 8 neutrons, some have 9 neutrons, and some have 10 neutrons. So in the air we breathe right now, we are breathing all three of those isotopes. And those are called stable isotopes. Stable meaning nothing happens to them over time. They just kind of hang out. And so if oxygen has 8 protons and 8 neutrons, its mass number is 16, right? 8 is 16. But if we have that other isotope that's 8 protons and 10 neutrons, well, that mass number is 18. So they have these slightly different weights to them. And it just has to do with how many neutrons they have. Now that's a stable isotope. We also have what are called unstable isotopes. You might know those better as radioactive elements. And like I said, later in the semester, we're going to talk a little bit about radioactive elements and what they can tell us about geologic history. But today, I just want you to know that they exist. And we'll talk more about specifics later on. Any questions yet? All right. Now, I did this whole chemistry review thing, and we're still in it, because I care about these elements and these atoms because they make up all of these rocks and minerals that we're going to be dealing with. And they make those up because they bond together and grow into those, right? As things, these atoms come together, they build our different rocks and minerals. And so to understand how that happens, we need to take a look at something called an ion. And an ion is an atom or molecule, a group of atoms, with an electrical charge. Earlier I said that all atoms have protons with a positive charge and electrons with a negative charge. And usually, or often, they can have the same number of protons and electrons. So overall, they have no charge. But if they gain or lose an electron, they're going to have an overall electric charge. And this happens because of those outermost electron shells I was talking about. Atoms, I know I'm personifying them, but atoms like them to be full. They like filled outermost shells. So if you would be a chlorine atom like this, the outermost shell has 7 electrons in it, and it really needs 8 to be complete. So that atom really wants 1 more electron. And over here, we have a sodium atom with 1 lonely electron orbiting in the outermost shell. And again, the atom doesn't like that. It wants that outermost shell to be full. So what can happen is an atom like this one will happily give up its electron. So now it gave up a negative charge. So it has a positive charge. Well, in this atom took that electron, so now it has an extra electron. It's happy because its outermost shell is full, but if it has an extra electron, it has a negative charge. And that's how we get ions that have a positive or a negative charge. If the atom has a positive charge, we call it a cation. You can kind of remember that because a T is like a plus sign, right? Plus for positive. And if you have an atom that has a negative charge, we call it an anion. And cations and anions are very important in building minerals. Any questions so far? No? You guys kind of remembering all of this from chem class? Maybe? No? That was like, if anything, it was at least, what, a few months ago? All right, so now that we know about these ions, now we can talk about bonding. And bonding is where atoms come together and stick together. And that's what makes our rocks and minerals, right? The atoms sticking together and growing together. Now, a very simple type of bonding that can happen, this is why I just went over the ions, is something called ionic bonding. And that's bonding between ions. We have all heard that opposites attract. And that's true. Positive and negative charges are attracted to each other. So an ionic bond is where you have your cation and your anion. Those opposite charges are attracted to each other. The classic example of this is with table salt, sodium chloride, or as you'll learn today, the mineral halite. Right? We already saw that sodium will happily give away an electron and chlorine will take it. So our sodium atom has a positive charge, our chloride anion has a negative charge. You put those together and it's an overall zero charge. Because that's the other thing in nature. Nature wants an overall zero charge. And so those things will bond nicely together and stick together. Ionic bonds are fairly easy to chemically break apart. Now, a stronger bond that exists is called a covalent bond. And a covalent bond is where atoms don't gain or lose electrons, they actually share electrons. So instead of an electron just orbiting one atom, it'll actually start orbiting two. And so that electron gets shared, and that makes for a stronger bond. And we have this example here of unhappy fluorine atoms that do not have their outermost shell filled, but if they end up sharing some electrons that start orbiting both of the atoms, then they feel like the outermost shell is full because they have those extra electrons orbiting them, and this is a much stronger bond than the ionic bond. If you take chemistry classes, you'll learn about some other bonds. You'll hear about hydrogen bonds and van der Waals bonds, and we're not going to go into all of those because they're not as important when we look at minerals particularly. But one that is important for minerals is called a metallic bond. And as the name suggests, it's common in our metals. And again, metals are things like copper and gold and such. And what happens in metallic bonds is some of the electrons move freely among many atoms. It's not, you have these electrons that aren't stuck in just one or two atoms. They kind of migrate and roam around freely through many atoms. They're not associated with any one specific atom. And this is also why metals can conduct electricity well, because you do have these electrons happily roaming. I don't have a really good illustration of that because it's like all this says is like this electron cloud doesn't belong to any one metal ion, so this electron might kind of wander around amongst several of those. Those are the three types of bonds I would like you to know for this class, but like I said, if you ever take a chemistry class, you'll probably learn about some more of them. So, any questions? Then let's talk about how minerals form. How do they come together? When they come together, they form through a process called crystallization. Right? I said one of the characteristics is that it's a crystalline solid. So crystallization is where your atoms bond together in this orderly internal structure. And I use salt a lot as an example because it's a very simple structure. It's easy to see. So what happens as salt crystallizes is you get a little sodium ion, and then a chlorine ion bonding to that, and then sodium, and then chlorine, and it just repeats over and over and over again, growing that crystal bigger and bigger. In some substances, though, we have what are called polymorphs. Now, this is another one of these words that I mentioned. We have lots of Greek and Latin root words in science, and this is one of them. Poly refers to many or different, and morph refers to shape or form. And so a polymorph, these are minerals with the same chemical chemical composition, so the exact same atoms make them up, but they have different crystal structures, right? That's where the morph, right? Different shapes, different forms. And this can happen because they form under different conditions. Maybe one forms at low pressure and one at high pressure. Could have to do with like temperature formation. But whatever happens, you get two different types of crystal structures. And this then can make for very different characteristics in your minerals. A classic example of polymorphs are with carbon, pure carbon. Pure carbon, I'm losing my voice, pardon me. Give me a moment. This happens a lot. You'll get used to it. Pure carbon can either be in the mineral graphite or in the mineral diamond. And there's nothing but carbon atoms in there. But the crystal structure is very, very different. And I gotta go get a drink. I'll be right back.
She needed to get some chug splashes, chat. Well, she gets some water. She'll be gone for like 15 seconds, and she's gonna come back.
All right,
She
that was
back.
quick. All right, so in graphite, all the carbon atoms are arranged in layers. And between those layers are very weak bonds. And so graphite is one of the softest minerals around. You can actually scratch it with your fingernail. Diamond, which has exactly the same composition, the little carbon atoms are bonded in a much stronger crystal structure, and it is the hardest substance. Nothing else can scratch it, only other diamonds. And so it's amazing where it can be exactly the same composition, but just the arrangement and the bonding of the atoms in the mineral can totally change the characteristics. Yes?
So what makes something a crystal?
What makes something a crystal is that regular pattern of atoms. Now we don't, sometimes you'll hear people like give you a mineral and say this is a crystal. Not all of them will show the perfect crystal shape, and that's just because maybe they grew in a place where, they grew up against something. So crystals don't always have to look perfect like that. Something can look like this and look kind of like a lump, but it's still crystalline because
I'm
the
looking at it right
atoms
now.
have that regular.
You can't be asking questions.
Does that answer your question? Any other questions? All right, so crystallization, this formation of these minerals coming in this nice regular orderly pattern can happen in a few different ways. One way you can get minerals crystallizing, one way you can get them forming, is solidification from a melt. Basically, something freezes. And for us, that's usually lava, right? Or some kind of liquid rock, right? The liquid rock's really, really hot, and then it cools down, and as it cools down, all the little atoms start arranging themselves and bonding with each other and forming a solid, and then we get minerals. So one way we can get a mineral forming is solidification from something that's liquid. You can also get precipitation from a solution. And this is where water in nature usually has stuff dissolved in it. And when that water evaporates, the water goes away and whatever was dissolved in it is left behind. This is something like when I was in grade school, it was like, ooh, we're in first grade. We're going to take water and we're going to pour salt in it and stir it up, and miraculously the salt disappears. Well, it didn't disappear, it's just dissolved in the water. And then we let the water sit out for like 3 weeks and it evaporated, and then the salt reappeared. Well, that reappearance where it comes out of the water, that's precipitation from a solution. This happens, like I said, when water evaporates, or it can also happen when hot water cools down, because hot water can hold a lot more material dissolved in it than cold water. So for instance, if you have a geyser or a hot spring, the hot water has a lot of stuff dissolved in it, but as that water cools, you'll start seeing minerals form. This is in a place called Badwater Basin in Death Valley National Park. The dark stuff you see is actually water, and it's just dark because there's dark rocks reflecting it. But the white is salt, because Death Valley is very, very dry. So any water that's there starts getting evaporated very, very quickly, and whatever is dissolved in the water gets left behind. And most commonly what's dissolved in water are different kinds of salts.
W joke.
And so this white is salt that is forming as that water evaporates. A weird way that you can get minerals forming is something called solid state diffusion. This does not happen here at Earth's surface. This happens actually deep underground when rocks get hot. When rocks get hot, what can happen is the little atoms are vibrating, and that can allow other atoms to kind of slip through and move around. It's a really weird process. And this is what creates metamorphic rocks and minerals. And so today I just want you to know that it exists. And when we talk about metamorphic rocks, we'll talk a little bit more about how and why it happens. We can also have something called biomineralization. Well, anytime you see bio in a word as a prefix, that means life. So biomineralization is where life helps a mineral form.
I'll try to.
I mean, we do that. Like, we have a mineral called apatite that coats our teeth. Another way you can look at it is you go collect shells along the beach. Well, those shells were created by clams and oysters and stuff like that. And the shells are made out of calcite or aragonite, which is a mineral. And corals count as biomineralization. The coral reef, basically there's an animal that's related to the jellyfish, but it takes dissolved material out of the water, it uses its food, and then it precipitates, it builds up that reef as a place for it to live. And so biomineralization is any of those things where some form of life helps create a mineral. And then our last thing that can happen is you can get something called fumarolic mineralization. And this is not common. This happens at places called fumaroles.
I thought she said funeral.
A fumarole is where a volcano is breathing. So volcanoes, even if they're not actively erupting, many volcanoes will give off hot volcanic gases. And where those volcanic gases come out of the ground is called a fumarole. And that's what we're seeing right here. See this hole right here? That's where we're on the side of a volcano and hot volcanic gas is coming out of that volcano. In fumarolic mineralization, what happens is a mineral, a solid mineral, forms directly from a gas. You know, usually if you go from a solid, you have to go solid, then it goes into a liquid, and then it goes into a gas. Or you go from a gas and it has to be a solid, and then a gas is liquid, a solid. In fumarolic, we skip the liquid phase. And so what's happening here, in this particular volcanic gas, there's a lot of sulfur, and all of this yellow is the mineral sulfur that's being left behind by the volcanic gases. You guys are familiar with dry ice, right? Yeah, this is kind of the opposite of dry ice, right? Dry ice goes from being a solid to a gas. This goes from being a gas to a solid.
Oh.
It just skips the liquid part. It's not real common, right? Because it only happens where you have volcanoes that are, active. Any questions? Don't stick your hand in there either. It's really, really hot.
Ooh.
Okay,
What's up, Sam?
In science, something scientists love to do is we love classifying things. And there are good reasons for that, because different things that are similar to each other will behave in similar ways. And geologists are no different from that, right? Biologists always classify like organisms into species and genus and all of that. We organize things into different types of minerals. And one of our big groups of minerals that we classify, that we put things into, are called silicates. And silicates are the most abundant mineral in Earth's crust. So pretty much anywhere you go on Earth's surface, if you pick up a rock or a handful of dirt or something like that, you are going to have at least some silicate minerals in there.
So
they are everywhere. What's that?
So what do they call it, silk?
No, silk refers to a size of particle, actually. Silica refers to the element silicon that's in all of these. And these are called silicates because they all contain a certain crystal structure called the silicate tetrahedron.
Locked it right now.
Okay, so silicate comes from the element silicon, and a tetrahedron is a shape that's formed. We're going to go into what the silicate tetrahedron is in just a moment. But I do want to point out that the other group of minerals that we have are called non-silicates. So, unlike in biology where they have however many thousands of genus and families and stuff, we have silicates and non-silicate minerals. Now, I said all silicate minerals in their crystal structure contain something called the silicate tetrahedron. A tetrahedron is a pyramid that has a triangular base. So in all of these minerals, they have this pyramid with a triangular base. In the absolute center of the pyramid, there is an atom of silicon. That's my little red marble in there. Okay? And then surrounding that, creating the rest of the pyramid, are oxygen atoms. So, I said it's a pyramid with a triangular base. All right, there's the top of the pyramid. Right, there's the top of the pyramid. If we look at the bottom of it, center of the oxygen atoms, it's a triangle, right? So that's going to be in every single silicate mineral. It's going to contain this group of atoms. Now, when we draw that and we draw crystal structures out, we get really tired of drawing this kind of chemistry thing. We call it the ball and stick model. So we kind of have a shorthand to show the silicate tetrahedron. We draw it as a triangle like this. Because right there is the top. Imagine you're looking down on the pyramid. There's the top of the pyramid, right? That's that top oxygen, and there's the oxygens that form the base. Make sense? All right. Now, in our silicate minerals, there are different kinds. There are different groups. And this is going to be something I go over today. I'm going to go over these different groups of silicate minerals, and you might be thinking, why is this important? We're going to see this pattern at least 3 more times in class. And so this is another one of those things, and you're going to find out this happens a lot in class. I'll introduce something one day, and then the next day we'll find out why that thing I introduced was very important. So today, I'm just going to introduce the different silicate minerals. Now, one group that you have isolated tetrahedra. So what that means is if we were to see this crystal structure, we're going to have little tetrahedra, right? And there's my shorthand. right? Where there's an oxygen, there's one, there's one, and the silicon would be sitting right in the middle of that pyramid. Overall, every silicate tetrahedra has a negative charge. So what holds it together is a cation that sits right there. Now in lab today, you're going to see an example of one of these called olivine. Olivine is a mineral that has isolated tetrahedra. Now, one thing about it though, is if all that's happening is there's this cation holding these little things together, that means this is not the strongest chemical bond out there. That means chemically, this can break down fairly easily. Now, that doesn't mean, when I say chemically, it doesn't mean if I hit it with a hammer, things are easy to break. I mean chemically reactive, like to water and oxygen, things like that. And because it's just held together by this cation, this is fairly easy to chemically break apart. That's a little bit different from this next one called a single chain silicate. And what happens in this one, we still, of course, have our little tetrahedra. Right? But now the oxygen that forms this part of this tetrahedra is shared by its neighbor. They're sharing oxygens. This makes this chemical structure a little bit stronger chemically. Because anytime we start sharing atoms like that, it's harder to chemically break apart. Now what I didn't draw in there, we do have to balance our charge, so there are still some cations in there. You'll see an example of this kind of mineral as well. We also have what's called a double chain silicate, and it's exactly what it sounds like, right? You have two chains that come together. I'm not going to draw this one out, but now look at this. If we look at this particular little tetrahedra, it is sharing oxygens with this neighbor, and this neighbor. So it's getting even harder to chemically break down. Then we have something called a sheet silicate. Sheet silicates, all the little tetrahedra line up in sheets. And in between these very thin sheets, there are weak bonds. So you will get minerals that look like this, that you can actually, if I do this carefully, you can peel them apart. And that's because the bonds are strong in 2 dimensions where all those oxygens are being shared, but they're weak in between those sheets. So you can kind of peel them. That's obviously a sheet silicate. And then lastly, we have what's called a framework silicate. I'm not even going to attempt to draw that, but what's happening is you have all kinds of these little tetrahedra in there, and every single one of the oxygens is shared with a neighbor. And so this is very, very strongly bonded together, very hard to chemically break down. And like I said, today this might seem like this is weird that I have to know this, but we're going to see this pattern several more times and see why it is important that we know these different groups of minerals. So today, know they exist. In a couple weeks, we'll see why it's so important. Any questions so far? You know, when I was in college, which was a long, long time ago, it was actually last millennium. It was really popular for people to get like tribal tattoos around their arm, and I got drunk one night when I was in mineralogy class, And I was like, man, the single chain silicate pattern, that would be like the most awesome tattoo. And so at like 2 in the morning when I got kicked out of the bar, I went to a friend's house. I live in a small town, really small town, like 6,000 people in the middle of the desert. So I went to a friend's house and I pounded on the door and I was like, I've got to go get a tattoo. And she's like, okay. And the closest place where you could get a tattoo is like 80 miles away in Albuquerque. And it's so funny that she's like just woke up and was like, okay, I'll drive you. And like 40 miles there, I sobered up and I was like, why am I in your car at like 2:30 in the morning and we're driving to Albuquerque? And she's like, you said you really needed a tattoo. And I was like, no, I don't. And so then she drove me home and put me to bed. And so I do not have the single chain silicate pattern tattooed to my arm, but for like half an hour in I don't know, 1990, it was a really good idea to me. So, the things you do in college.
Chad, is this real?
Yeah. I sobered up really quick.
Chad, this is not real. Don't let Queso eat the classroom? Yes, he's eating me up right now.
All right, those were, we went over the silicate minerals, but I mentioned that we also have these non-silicates that do not have this silicon and oxygen structure in their crystals. Non-silicates are not as abundant. In fact, some of them are actually quite rare, but they are still important to us. So I'm going to go over the groups of non-silicates, and after I do that, we're going to take a look at why they're important to us. So one group are called the carbonates. They all have this ion, the carbonate ion, CO3 in them. A great example of one is calcite, which is calcium carbonate. And calcite is used to make things like the cement that holds these bricks together. It's used, if you take medicine and you take pills, it's used to kind of hold the pills together. It's used to make concrete roadways. That kind of stuff is what calcite's used for. We also have a group called halides. Halides either contain chlorine, fluorine, or bromine. They don't contain all of those, they contain one of those. And a good example, I've been using it all morning, is sodium chloride, which is the mineral halite. It's salt. And salt is used to flavor and preserve food. Calcium it's used carbonate. To de-ice roadways. It's used for some industrial processes. We also have what are called oxides. These all have this oxygen in them. A good example is iron oxide or hematite. Hematite is mined to make steel. So the steel that holds up this building, or if you have a car that has a cast iron engine block, all of that probably began as a mineral like hematite. Yeah.
Is that why metals like that are magnetic?
Sometimes you just gotta ask.
Magnetism comes from something else, but yes. So hematite is often magnetic because it does have iron in it.
Okay.
Bro, I don't even know what calcium carbonate is.
You can also have sulfides. Sulfides will all have sulfur in them. An example is lead sulfide, which is galena. In your car, when you started it this morning, there's a battery that turns the starter. That's a lead acid battery. Guess where they get the lead from? Yeah, it comes from things like galena. We also have sulfates. They all have the sulfate ion, which is SO4. A good example is calcium sulfate, which is gypsum.
I'm just trying to lock in.
The walls in this building, drywall and plaster, are made from gypsum. And then you have the native elements. Native elements, when geologists use the term native, it means pure. So if I say native silver, native copper, native native carbon, if I use that word native, it just means pure of something. And so I give you the example of gold. Native gold is pure gold. It is, of course, a lot of people think jewelry, right? but it's also used in lots of electronics. Lots of our electronics work because there is some gold in there. So now I'll say I went over the different kinds of non-silicates. Why are they important to us, even though they're not the most common?
They make things function.
Exactly. We use these to make all kinds of different things. Now we use some silicates to make stuff too, but lots of things we use in our everyday lives come from these non-silicates.
So these are like rare earth minerals?
So yes, so rare earth elements. Rare earth elements are a group of elements that are really important today because I see lots of you have phones and tablets out. The transmitters in those will not work without rare earth elements. And so some rare earth element or minerals that contain rare earth elements are like columbite and things, and they do fall into some of these. Any questions? All right. You are going to have a lab today. You're going to start a lab today. That's the better way of putting it. You're going to start a lab today, and in this lab,
This class ends in like 2 hours.
You're going to be given, well, there's something like 7,000 different
Kobe
minerals
Bryant.
that exist today. And I'm losing my voice again. It's not good. It's the beginning of the semester. But there's something like 7,000 different minerals. So is it fair to make you learn half of them? No. Good answer. There might be 7,000 of them, but only say about 50 are common. I'm going to have you guys learn about 25 of the really, really common ones, and then a few of the ones that maybe aren't that use them a lot for things. So you'll be given about 30 minerals that you'll have to identify. And I'm not just going to be like, here they are, good luck. I'm going to give you in the lab a flow chart where it basically asks you questions like, check this characteristic, and if it's this, follow this pathway. If it's another thing, follow this pathway. And so you'll be following kind of pathways that show you how to identify the minerals. And it's basically options that once you get good at it, you just do in your head. But I don't expect you to do that yet. So you'll be given these nice little flow charts of what characteristics to look at. Now, usually when I ask students, what characteristics should we look at in minerals, the number one thing they say is the color. Because they have pretty colors, right? Color is really not good. Because every one of those minerals I have shown right up there are exactly the same. Those are all quartz.
Okay.
Some minerals come in
Bye-bye.
all kinds of different colors. And some minerals, these are all three different ones, they're the same. So please don't use color as your first choice for identifying minerals. Look at other characteristics first. Now, that being said, there are a few things, like this particular one, that is always this color. You'll figure it out. So, we're not going to use color, but what other characteristics are we going to use? What do you think? Structure, like the shape it has? Very good. That's the crystal form. Excellent.
The hardness.
The hardness of something. Very good. Anything else? Texture, like what it feels like? Some of them will have, well, most of them will be about the same, but a few will have a different feel to them. All right, let's look at these characteristics that we're going to use. So, don't use color as your first thing. You can use it when you get down to the last, right? But don't be like, oh, it's green, it has to be quartz, because there's like 14 other green minerals out there. You can use something